Hey students, welcome to lesson 2 here in Unit 6, still talking about unit circles and triangles and all kinds of good stuff and seeing how these things relate to each other. This one starts off with a notice and a wonder, so take just a moment to maybe notice and wonder some things. Maybe if your teachers doing this together in class, you'll be adding some ideas to a Jamboard or a question on Google Classroom. Thinking about actually what we just did in lesson 1, I know I noticed a couple things. I noticed that C is the hypotenuse. Of this triangle. Triangle ABC. And I also noticed what looks like, I can't quite tell for sure if A is at the center, but C also looks like radius of the circle. And call that circle A, like that. I notice that angle A is opposite side A. That might be something you remember from geometry, that we name our angles and our sides opposite each other. That means they're all the way across the triangle. The side is opposite the two sides that make up the angle. And we can say that for all of our other ones too, like angle B is opposite side B. Angle C is opposite side C. I can tell that point B is on the circle. And I can also tell that we used some of this information in our last lesson, that if we start here like with a coordinate grid, B and A would be the coordinates of point B. So the length of B and an A, so remember the x's come first, moving side to side comes first, and then we would drop down. So looks like B negative A would be the coordinates of it. Maybe you're wondering some other kind of stuff. I'm not quite sure what else you might be wondering or noticing, but there's definitely some things to get you started as we think about that. As we recall some right triangle trigonometry, yeah, definitely need some recall on this one. You might be remembering some things like this sine and cosine and tangent. So there are lots of ways to remember sine, cosine, and tangent. We use this thing called theta, usually for angles. I'm pretty sure that that's what they're using in here too throughout our unit. I'm just going to take a quick gander through. Looks like they use a lot of letters to name them. We could also just call it like sine x or sine, whatever it might be. Sine is an operation in math, just like division, multiplication, log, things like that. So sine, cosine, and tangent relate the opposite, the adjacent, and the hypotenuse. So perhaps you're remembering SOHCAHTOA. So sine is the opposite over hypotenuse. Cosine is the adjacent side over hypotenuse. Remember, adjacent means next to or nearby. And tangent is opposite over adjacent. Lots of ways to remember that. SOHCAHTOA is how some people remember it. So toa. Anyway, however you go about doing it. We need to find the cosine of A, the sine of A, and the tangent of A. So I'm going to use this information right here going through that. So we have angle A here. In your math class before, you probably started with just naming those different sides. So remember that the side opposite angle A, our hypotenuse is always the longest one, or the one opposite the right angle. And the adjacent is the one next to it, right next to the angle that isn't the hypotenuse. Okay. So now that we have that, we should be just plugging and chugging here. So our cosine of A, cosine is adjacent, which in this case is 15, over the hypotenuse, 17. The sine of A, angle A, is the side opposite angle A, which is 8, over the hypotenuse, still 17. And the tangent of angle A, now I keep on saying angle A for this because if we change which angle we're working with, the opposite and adjacent sides are different. So you always have to think about what angle you're starting with. Tangent of A, opposite of A is 8. Adjacent to A is 15. And now we've got some neat ideas going on there. So question 2 takes us to a different place. It says to sketch a triangle DEF where sine of D equals the cosine of D, and E is the right angle. So if the sine and the cosine have to equal each other, that means that opposite over hypotenuse has to equal adjacent over hypotenuse. If the sine has to equal the cosine. And we've seen this before, definitely already, that if the denominators have to equal each other here, right, have to be the same hypotenuse, the numerators also would have to equal each other. So this is telling me that the opposite side and the adjacent side would have to be the same length. Whatever those two sides are, they have to be the same length, and we have to have a right angle in between. So if angle E is the right angle, there it is there, that makes this our hypotenuse. Really, either of these two other angles could be angle D, because it really doesn't matter, because the opposite equals the adjacent, and these two sides are equal in length to each other. You might remember those kind of tick marks that tell us that they are in fact equal. So we sketched a triangle DEF. E is the right angle. The sine would equal the cosine because they're equal lengths. What is the value of tangent D for this triangle? So tangent D, if it equals the opposite over the adjacent, and if the opposite equals the adjacent, that means we have the same number over the same number. Whatever that number is, maybe it's 7 over 7, or 15 over 15, or 2,000 over 2,000. But anytime we have the same number over the same number, this tangent would equal 1. And we know that because the opposite and adjacent sides must be the same length. They had to be the same length because the sine had to equal the cosine. Number 3, let's move on through. We're almost done with this section. That's pretty awesome. If the coordinates of point I are 9, 12, what is the value of cosine G, sine G, and tangent G for triangle GHI? Explain or show your reasoning. Well, it gives us some ordered pairs already to begin with. All right, so we know that G is at the origin. To H, this is our length of 9 right here. And that means our height of this triangle here would have to be 12. And so it's asking us what are the cosine, sine, and tangent, sine, cosine, and tangent. I don't know the length of this hypotenuse. So we have to calculate that first because for both sine and cosine, we need the hypotenuse to write that up. Now, if you watch my other video, you know one of our very famous triples is a 3, 4, 5 triangle. I can use Pythagorean theorem and do 9 squared plus 12 squared equals c squared, and I can solve that out. But I noticed this 3, 4, 5 relationship going on here. So if I take 3 and multiply it by 3, I get the side length of 9. 4 times 3 is a side length of 12. So my last side length, I'm just kind of trying to be an efficient mathematician. Remember, I'm not lazy, I'm just efficient. There's a big difference. I just found out that my hypotenuse is length 15. So again, I could do 9 squared plus 12 squared, and it would be our c squared. But I already figured that out, so I figured it twice. Cosine, sine, and tangent of G. Cosine is, I'm looking up top, adjacent over hypotenuse. Hypotenuse is 15. From angle G, the adjacent side is 9. So 9 out of 15. We can reduce that because 3 goes into each of those evenly to be the same as 3/5. See the 3, 4, 5 triangle and how much we're going to use this now? Sine of angle G. Sine is opposite side, being 12 over 15, still the hypotenuse. 3 goes into both of those. Goes in 4 times and 5 times. There's our 3, 4, 5 triangle. I want to take a bet about what we're going to find with G. Opposite side is 12 over the adjacent side, which is 9. 3 goes into both of those. There we have it.